Hello everyone, I welcomes all of you to this lecture. So in last lecture we have started with some static characteristics of an instrument. Okay, so under that we have completed number of points, number of characteristics. So we have seen that characteristics may be static or dynamic. Okay, so out of that we have started with some static characteristics. We have seen some static characteristics, and these characteristics are very important because it will give you the idea about that instrument's functionality, which is very important. So while using any instrument you must know about different characteristics like static and dynamic of that instruments. Okay, and these characteristics clearly defines the use of that instruments in a particular applications. Okay, so we must know what is the threshold value, what is the error inside that. Okay, so what is the accuracy, precision. So all these things are very important. Okay, so there are n number of characteristics that we have started with, and with continuation in that, let's move forward with some new characteristics. Okay, so today's first point is a drift. Okay, now this drift is again very important parameter. So what do you mean by drift? Let's see. So if you see here, the drift is defined as the gradual shift in the indication over a period of a time wherein the input variable does not change. Okay, so in short I can say that the drift is nothing but a gradual shift in the indication or in the output. Okay, over a period of a time, that is very important. Okay, so because over a period of a time you may get this drift. Okay, so it is over a period of a time where input variable does not change. The meaning of this line, the input variable does not change, means what? It may be linear, there may be a linear change in the input, but as per that linear change there must be a linear output change, but there are some shift in that, and that we have to see. So if you see, it is an undesirable quantity and it cannot be completely compensated for. Okay, so yes, you can do some arrangement for that, but it cannot be completely compensated. Okay, so which are the causes of this? So I think you know the stray capacitance like quantities. So inside this there may be a stray electric field, stray magnetic field. So due to this there may be a change in some inside parameters of the instruments. Okay, so there may be a thermal EMF. Okay, so I think your physics is very well, so you must know this thermal EMF and all this stray capacitance, electrical field, stray magnetic field, and all this. Okay, so these are the causes: the stray electric field, stray magnetic field, then thermal EMF, then there is a change in temperature, and then mechanical vibrations, etc. Okay, so these are some causes, some important causes which are listed here. Okay, so we can do some arrangement for that we will see afterwards after studying different types of drifts, but you cannot completely remove this gradual shift. Okay, so that's why after some period of a time you have to do the calibration of the instrument. And what do you mean by calibration? That also we have discussed in last lecture. Okay, so that's why this drift is again undesirable quantity and which must be reduced properly with the help of some arrangements. Okay, so these are some causes that are listed here. For example, if you see the changes in the temperature, so if you see any instrument, that instrument contains different types of we can say resistive element inside that. Semiconductor elements are there. Okay, so if you see any semiconductor element that is very sensitive to temperature, so if you see the semiconductor material, if you increase the temperature surrounding it, there may be a badly effect in its resistance, and in turns that we are getting a change in the current. Okay, so and that may be harmful or that may be undesirable. So that's why this temperature is making some effect in most of the instruments. Okay, so therefore there are some arrangements inside that which are done to keep the temperature at normal level, or to reduce the power dissipation, we can say. Okay, so some heat sinks are used inside the your computers, or you can say some fans are used so that the temperature must be what we can say, the at the normal level. Okay, so or to reduce that temperature, that arrangement is done. Okay, so that temperature is again most important parameter which is responsible for this drift. Okay, so there are some mechanical vibrations. If suppose the instrument or any system is having some vibrations, then there may be a drift also at the output. Okay, so let us see which types of drifts are there and how to reduce that. Okay, so let us move forward. Now if you see, there are two types of drifts, 2 to 3 types of drifts. One is a zero drift, another is a sensitivity drift, and the third is a combination of this both. Okay, so drift or a zero drift is a variation in the output of an instrument which is not caused by any change in the input. Okay, so it is commonly caused by internal temperature changes and component instability. Okay, so this temperature changes causes the component instability, we can say. Okay, because most of the components are affected due to the temperature changes only. Okay, yes, of course there are another reasons which are there which causes this component instability, but the temperature is most common change, so we have to take care of that. Okay, so this is zero drift, which is a variation in the output of an instrument which is not caused by any change in input. That is very important. Okay, means what? Yes, of course there is a linear change, but that drift is not caused by this linear change. That is due to some internal temperature and component instability. Okay, so if you want to see the graph of this, then if you can observe this left graph, the first graph. So here this graph is input versus output. Okay, and this is our desirable output, or we can say standard output curve, input versus output curve. So if you see, it starts from 0 here and it is increasing linearly with respect to time. As we go on increasing the input, we will get the output. Okay, so this is the input axis, this is the output axis. Okay, but if you observe here, this is the, we can say, the real graph that we are getting here. This is the desired graph, we can say, and this is the real that we are getting. So here we can say that this is the zero drift. Okay, so this at zero also I am getting some output at this point. Suppose it is 5 units. So at 0 also I am getting a 5 unit in actual graph. So this is called as a zero drift, because we have not applied any input here, and then also we are getting the output. And whenever we are applying the input and we are go on increasing linearly with this input, then what happens? The output will also increase, but it will be added to that drift. Okay, and if you see this desirable, or the, we can just say, standard or perfect graph, we can say, so it is starting from a 0 itself. There is no any error inside this. Okay, so I think you got the idea about this. So this much output is present without applying any input here, so that is called as a zero drift. Okay, and that is due to the internal temperature changes and the component instability. Okay, so let us see the next point, that is a sensitivity drift. So sensitivity drift defines the amount by which instrument sensitivity varies as ambient conditions or ambient temperatures, like quantities like temperatures changes. Okay, see what is the definition? It is the amount by which instrument sensitivity varies. So sensitivity varies here. Okay, that is the important point that we have to denote here. So here let's see the graph of this. This is the input versus output graph, and this is the sensitivity drift. See here, at 0 input, of course it is giving a 0 input, but what happens here is that as we go on increasing, we are changing the input. What happens here is that here the sensitivity varies as some ambient condition changes, like a temperature or any other things. So here it is expected that we should get a graph like this, but due to some internal sensitivity changes, what happens here is that there is some gradual drift like this. Okay, so this is called as a sensitivity drift. Okay, so another name to this is a span drift. Okay, so it is also called as a span drift. So you can either call it as a span drift or a sensitivity drift. Okay, so it is all about the sensitivity drift, which is changing, which causes due to the variation in the sensitivity. Okay, so I think you got the idea about this. That is the sensitivity drift. Okay, now there is another type of drift which is called as a combination of this zero drift and sensitivity drift, which is also called as a zonal drift. So if you see this graph, this is the zonal shift graph, we can say. Okay, so zonal graph is nothing, zonal shift zonal drift is nothing but combination of a zero drift and sensitivity drift. So from this diagram you can easily identify this. So here this is my desired output, so this is my input axis and this is my output axis. So as per the input, this should be desired output, but there is, of course, there is a zero drift present over here. At zero also we are getting some output, but as we go on applying the inputs, okay, so there is change in the sensitivity. So here zero drift is available as well as the sensitivity drift is available. So these two drifts gets added over here, and we are getting a zonal drift. Okay, so this is more harmful than these two, because it is combination of these two, and it will cause to the undesirable output changes. Okay, so that's why we have to make some arrangements to reduce that. Okay, so let us see one example that clearly shows you how the zero and sensitivity drift affects on instrumental characteristics. Okay, so this is the zero and sensitivity drift effect on instruments characteristics that we have to see. Suppose this is the strain gauge type of instrument, or any type of instrument. Okay, so here it clearly defines or shows you the variation of input and output, input versus output, we can say. Okay, now here this Q out. Okay, so this Q out shows the calibration curve at nominal design temperature measured value. Okay, and if you see here, this is the actual operating curve at of design temperature curve. Okay, so we can say this is our desired curve. In short, I can say, okay, desired curve of strain gauge output versus input, or input versus output, and this is the actual operating curve at of design temperature curve. Okay, or at of design temperature curve. Okay, so this is my actual operating curve, and if you see here, this much is a total error due to zero drift and sensitivity drift. Okay, so and if your measurement is very sensitive, and if there is a huge effect, if the huge effect at the system's output when there is small error, then at that time there may be very harmful. They may be very harmful for our applications, such instruments. Okay, so that's why it must be reduced. Okay, so if you see the strain gauge, we can say that the ambient temperature changes the causes change in the resistance of the strain gauge. Okay, so what happens here is that I am talking about just a strain gauge here because I am giving you an example. So the ambient temperature changes the resistance of this strain gauge, and we know that the resistance or change in resistance is the most important parameter in a strain gauge measurement. So that may affect your readings. Of course, it may affect your readings. Okay, what happens here is that inside that we are generally using a bridge, and the bridge circuit becomes unbalanced here, and as a result of this, there is an output drift. So it may be a combination of zero drift and we can say sensitivity drift. Okay, so this resistance changes also affects the sensitivity or scale factor of the instrument, and as its scale factor affects, what happens here is that we are getting a false reading at the output. Okay, so here the total error is due to the drift, which is the combination or combined effect of a zero as well as a sensitivity drift. So it affects some factors inside that. Okay, so if one parameter is changed due to the temperature or any other parameter, it may affect number of parameters inside that, and that will be very harmful, and it will give a false readings. Okay, false readings. Okay, so that must be reduced. So of course it cannot be eliminated or reduced, and it is observed, or we get that error or that drift over a period of time. So that's why calibration is needed, no doubt. Okay, but some other things or some other adjustment or arrangements that we can do here. So what we can do is that the stray electrostatic or electromagnetic fields can be prevented from the affecting the measurement by proper shielding. Okay, so you have to do some proper shielding for that, so that we can reduce or prevent some electrostatic or electromagnetic or electric fields or stray magnetic fields, we can say. So proper shielding is one option. Another option is that suppose you are having some mechanical vibrations Okay, so no, most of the devices will be having this problem because instrument is not vibrating. But suppose it is fitted on some vibrating instruments or some other vibrating systems, then it may affect. Okay, so at that time what we have to do is that the effect of this mechanical vibration can be reduced by proper mounting. So you have to do some proper mounting or proper setting over there, then this mechanical vibrations can be reduced. Okay, so temperature changes is one another important parameter. So already I have discussed about that. We have to use some heat sinks or some, what we can say, temperature conditioning circuits we have to use there. Okay, so for example in laptop there is a fan or heat sink, or you may have seen different types of power transistor. There is some metallic structure is there like aluminum which is absorbing the heat. So like this we can do some arrangement. So these temperature changes must be avoided using proper method that you can do. And the most important thing is that the instrument must be a standard instrument. Means what? The components used in that instrument must be of high quality so that they maintain the required characteristics during the period of operation. If you are using some we can say faulty components or low quality components, then what will happen? Then they may what we can say burn quickly, or they may give you output after some short period of time. Okay, or they may get damaged quickly. So that's why it is recommended that you have to use the standard components inside that. Okay, so this is all about the zero drift and sensitivity drift. Okay, so this we have seen. So let us move forward with next point, that is error. Okay, now this is most important parameter of any instrument, because we generally we call that the system should give you a errorless output. Okay, so means what? There should not be any error. Okay, the actual output and standard output must be equal. But if any instrument is giving you an error, means what? It is of no use. So that's why we must reduce that error again. Okay, so that's why this is the most important parameter. So we have to see again the broad classification of this error afterwards, after completing this static and dynamic characteristics. But for the sake of time, just see only the definition of this error, and after that we will see different types of error presents in the instruments. Okay, or measurements we can say. So let us see the error. It is the deviation of the true value from the desired value. Okay, so if the output is deviating from the true value, then it is referred as an error. So such error is called as a static error generally. Okay, so there are n number of types of errors that we have to see afterwards, but just see the basic definition of error in this lecture. Okay, so after completing static and dynamic characteristics, we will see broad classification of errors. Okay, so different types of errors. So it involves comparison of unknown quantity with an accepted standard quantity. Okay, so just we have to compare that unknown quantity with standard quantity, and if it is equal, then we can say that there is no error. If there is some deviation, of course there will be an error. Okay, so during calibration this process is done. Okay, the degree to which an instrument approaches to its expected value of is expressed in terms of a error of an instrument. Okay, so if you see the errors, it may be either absolute or percentage error. Okay, so let us see what do you mean by that absolute error, what do you mean by the percentage error, and let's see some mathematical expressions of that. Okay, so let us see what do you mean by absolute error. So absolute error is the result of comparison between the expected value of the variable and the observed value of the variable. Okay, so whenever we are doing some measurements, we are expecting some standard values or some we can say that desired value or desired value of the variable, and actually we get something that is called as the observed value. So just we have to do some mathematics with that, and we will get that absolute error. So what do you mean by absolute error? Again, see the definition. It is comparison between expected value and observed value of any variable that you are using in your applications. So mathematically error can be given as AT minus AM. Okay, so where E, small e is error, where AT is expected value of a variable, and AM is the measured or observed value of the variable. So 80 is expected value, T for expected, and M for measured. Okay, so if you see the percentage error now, okay, it is defined as the ratio of absolute error to the expected value of the variable when expressed in a percentage. Okay, so whenever you take that absolute error, that is nothing but the expected value minus that observed value, that is called as absolute error. So whenever you take that absolute error with some expected value that you have used in your equation and you express in percentage, then that is called as a percentage error. Okay, so here in this case, the percentage error or percent error, we can say it is given by the absolute error divided by expected value. So where the absolute error is denoted by E, which is nothing but 80 minus AM. Okay, so expected value absolute value divided by expected value into 100. So it can be denoted by E divided by 80. 80 is expected value into 100. So here E can be replaced with 80 minus AM divided by 80 into 100. So finally the percentage error is equal to 80 minus AM divided by 80 into 100. Okay, so this is all about the percentage error. Okay, but if you see, it is more frequently expressed as accuracy. I think we have seen the accuracy, we have seen the precision, we have seen the difference between that accuracy and precision. Okay, you know very well the accuracy, and this accuracy and errors, these are interrelated quantities, because accuracy and errors, from accuracy we can say the error, and from error we can say what is the accuracy. Okay, so that's why they are interrelated. So that's why it is more frequently expressed as accuracy. We are talking about this percentage error rather than error. So this percentage error is frequently expressed as an accuracy rather than error. Okay, so thus the percentage error is called as a relative percentage error. See this definition. This percentage error is also called as what? Relative percentage error, and therefore these two quantities are interrelated. So that's why I can say that accuracy is equal to 1 minus relative error. So if you see the relative error we have calculated over here, that is E divided by 80 into 100, that is nothing but 80 minus AM divided by 80 into 100. Okay, so that's why accuracy is 1 minus relative error. So for this relative error, just we have to remove this 100 and we have to put the value of this 80 minus AM divided by 80, that is the value of this one. Okay, relative error. Okay, so that's why we can say A is a relative accuracy, so and A is given by 1 minus 80 minus AM divided by 80. Okay, so finally if I want to calculate the accuracy in percentage, just we have to calculate this relative accuracy and after that multiply that with 100%. Okay, so it will give you a percent accuracy. So finally the percent accuracy is equation that I am getting here, that is in bracket 1 minus 80 minus AM divided by 80 bracket complete into 100%. Okay, and here the error can also be expressed as a percentage of the full scale reading. So the error can also be expressed as a full percentage of the full scale reading. Okay, so that also we have to see. Okay, so let's take one example, and in that example you can get the real, we can say, meaning or understanding of the given quantities. Okay, or the different types of errors that we have discussed now. Okay, so let's see that here here example is given. The expressed value of the voltage across a register is 80. However, the measurement gives a value of 79 volt. Okay, so calculate absolute error, percent error, relative accuracy, then percentage accuracy, and the next is error expressed as a percentage of the full scale reading if the full scale deflection is 0 to 100 volt. Okay, so let's see that. What we have to do is that here we have to calculate all these 5 quantities here, and the expected value across the register is 80 volt. These are two important parameters, 80 volt, but while doing a measurement we are getting something 79 volt. Okay, so now we have to calculate the absolute error first. Okay, so in this case, what do you mean by absolute error? It is 80 minus AM. So what do you mean by 80? That we have seen AT is what? It is expected value. And what is AM? AM is measured or observed value. So here AT or expected value is 80 volt, and the actual measured value is 79 volt. Okay, so what do you mean by obsolete error? It is just the difference between that expected and measured value, and that is 80 minus 79, so that is a 1 volt here. Okay, now let's calculate the percentage error. That is the second quantity that we have to calculate here. So percentage error is nothing but 80 minus AM divided by 80 into 100. In other words, expected value minus measured value per expected value, or divided by expected value. So here 80 is expected value minus 79 is measured value divided by expected value is 80 into 100. So in terms of percentage, it is 1.25%. So percentage error is 1.25%. Okay, so that is calculated over here. Now what do you mean by relative accuracy? That we have discussed earlier. This relative accuracy is given by 1 minus 80 minus AM divided by 80. Okay, now here we have to do 1 minus 80 minus 79 divided by 80. Okay, so 1 minus 1 divided by 80 that we are getting here, and the relative accuracy that we are getting here is 0.9875. Okay, so just see here, just do some reverse engineering, and if you want relative accuracy as 1, then do reverse engineering and see which value you require as we can say expected and measured. Okay, so that you can do also. Okay, so here suppose let's see that suppose here measured value is 80 and expected is also 80. So what will happen here? It will be 80 minus 80. So here it will be a 0 divided by 80. So 0 divided by anything is 0. So finally you will get 1. So relative accuracy is 1 only when, we can say that, only when the expected value and this real value are equal. Okay, so there will not be any error at that time. Okay, so this 80 minus 80 will be 0, so there will be 0 error. Okay, absolute error will be also 0. So we can say that whenever there is a 0% error and 0 absolute error, the relative accuracy is 1. So this is a reverse engineering that I have told you now. Okay, so how to calculate the percent accuracy? So it is just relative accuracy into 100%. So what is the relative accuracy? That is 0.9875, that is multiplied with 100. So here percent accuracy is 98.75% that you are getting here. So it is percent accuracy. Okay, now this for last point, that is point number 5, that is very important. Here error expressed as a percentage of the full scale reading if the full scale deflection is 0 to 100 volt. So here percent error expressed as a percentage of a full scale reading that we have to calculate. So full scale deflection is 0 to 100 volt means what? It is 100 volt, and it is nothing but 80 minus AM divided by full scale deflection. So here in this case it is 80 minus 79 divided by 100, and we have to calculate in terms of a percentage, so that's why it is multiplied by 100. So 100 and 100 gets cancelled, and finally 80 minus 79 we are getting 1%. So here I can say that for full scale deflection of 0 to 100 volt, the percent error expressed as percentage of full scale reading is 1% here. Okay, so this is all about the calculations that we have done. Okay, so in this lecture we have completed these two important parameters, that is drift and that is error. Okay, so again I am repeating, this is the simple definitions of error. Again there are n number of types of errors that we have to study separately after completing these characteristics, and with the completion of that error types we will complete this unit number 3, maybe in next lecture or after that next lecture. Okay, so it is all about the drift and error that we have studied now. Okay, so this unit is purely theoretical, and there are some important parameters which are covered here, like static characteristics, dynamic characteristics, and all these different types of errors which are very important. Okay, before studying any instrument. So that's why we have in next lecture, or sorry, in next unit or next to next unit, we have to see these different types of instrument there. So that's why while studying that instruments, you must know different types of characteristics of an instrument, like a static and dynamic. So that's why we have covered this. Okay, so in next lecture we will start with some new points. Okay, just study this, revise this, make your notes. I'm giving you time to make a notes and clarify your doubts. Okay, if you have any doubts, you can ask me. Okay, so for today's lecture we'll stop here. Thank you very much. Thank you.